Welcome to the end of Chapter 7 class. Today is going to be our final notes for 7. We're moving on to something called the natural logarithm. Now, we've already talked about a concept similar to this, the common logarithm. So the common logarithm, essentially, if I write just a log, you know is talking about a log base 10. All right, that's one of our assumptions. It's called the common logarithm. Well, there's another one that does that. Another one that the calculator is actually really good at calculating for you. It's called the natural logarithm. What the natural logarithm means is you're taking a log base e. Again, we haven't had that much time to talk about the importance of e, but you've seen it before. When we talked about continuously compounding interest, that used e. All right, so remember, e is a legitimate number, 2.717. And then it keeps going on forever just like pi does. Now, the cool thing about today, we're not really learning anything new, all right? All we're doing is we're reviewing every concept we've done with logarithms, and we're applying it to natural logarithms to show you it still holds true. First thing to understand, it is the inverse of y equals e to the x. Now, I'm not going to make you graph anything. We've already covered graphing in this section, but I just wanted you to be aware to make sure you understand it is the inverse of that function, all right? Now, let's recall condensing natural logarithms. So condensing works exactly the same way as it did before. So the first thing I'm going to do when I'm condensing, I'm going to take any multiplier, any coefficient, and I'm going to pop it up as a power. So that's going to turn into the ln of 15 squared, which means the ln of 225 minus the ln of 75. Then I want you to notice the subtraction. Remember, subtraction means division. So I'm going to end up dividing those two. 225 divided by 75, and that's just going to turn into the natural log of 3. So again, all the same rules still apply. Looking at the next one, again, I'm going to bop up every coefficient. So this will become the natural log of x cubed, natural log of y squared, and 15. And what I want you to notice, now we are adding between all of those terms. When you're adding between the terms, you end up just creating a chain of multiplication. And then that will be your final answer. Here I see some multipliers again that need to be brought up. So this will be ln of x cubed, ln. Now when you square 2x, remember to square the 2 as well. Don't forget that that will become a 4x squared. That subtraction is going to turn into division. All right, now x squared, or x cubed divided by x squared. 3 take away 2. Remember, you can simplify that down to an x. So I'm going to have the natural log of x over 4, having this written in condensed form. All right, so again, same thing as what we've been doing, now just applied to a different type of logarithm. You also solve a natural log equation the same way. You're going to switch it into exponential form. Now the thing to remember, natural log, the thing to remember is you have a base e you're working with. So when you do Mr. Loopy, e squared equals x. Okay, so when you're doing Mr. Loopy, remember you're dealing with a base e. Now, just not like natural logs, all this stuff, remember e is a number. E squared is actually a legitimate number. It's the number 7.39 approximately. Now, I don't want you to write that out. I want you to leave it as e squared. But just I want to emphasize the fact we're dealing with a number. This is a numerical solution just like everything else we've been doing. for our next one. Now this one, we can simplify this first. Remember when we're solving these, if you can condense, you have to. And recall, addition turns into multiplication. So that turns into the natural log of 6x equals 2. Now I'm ready to use Mr. Loopy in order to solve this. E squared equals 6x. So if I want x by itself, that means I have to divide both sides by 6. So x is going to be e squared divided by 6. All right. So now something that actually ends up easier when you're dealing with natural logarithms are solving exponential equations, because a natural log is a direct inverse of these. So what does that mean? Well, that means that when I take the natural log of both sides, it actually just wipes out that e. So, kind of interesting. That actually makes it a little bit easier for us. So, natural log it. So the opposite side gets natural logged. The e just goes away, and you're just left with your exponent. So that's kind of the new thing for this one. It's actually easier than what you've been having to do before. Add 2 to both sides. And there's our answer. All right, now it is important though, before you natural log both sides, you do want to make sure that it's as simplified as possible first. So what that means is you want to turn this into e to the 3x equals 10. Now you want to natural log both sides. That gets rid of your e, turns that into a natural log of 10, and then divide by 3. And there's your answer. Okay, or in this case, you want to subtract 2 from both sides, divide by 4. So 14 divided by 4 is 3.5. Now, ln both sides, divide by 2, and there's your answer. So solving these exponential ones when you can use a natural log actually turns out a whole lot easier than it ever was before. All right, so we are nearly there. We're nearly done. Just one more example, and then you'll be done with your Chapter 7 notes completely. So, a spacecraft can attain a stable orbit 300 kilometers above Earth if it reaches a velocity of 7.7 kilometers per second. The formula for a rocket's maximum velocity in kilometers per second is v equals negative 0.0098 t plus c ln of r. The booster rockets for t seconds and the velocity of the exhaust is c kilometers per second. The ratio of the mass of the rocket filled with fuel to its mass without fuel is r. Suppose a rocket shown in the photo has a mass ratio of 25, a firing time of 100 seconds, and an exhaust velocity as shown. Can the spacecraft attain a stable orbit 300 kilometers above Earth? All right, so the first thing is we need to plug everything in. All right? So let's plug in all of our information so we can find the velocity. So negative 0.0098. Now it says that t is how long the rocket fires for. And here it says there's a firing time of 100 seconds. So I'm going to put 100 in there. Plus c, well, it says that c is the velocity of the exhaust. And it says that's from the photo. So that's going to be 2.8 natural log R. And R is the mass ratio, which is going to be 25. So all we're really doing here is picking out important information. Now that is something we can just type into the calculator. That's just one giant number. So that's what I'm going to do. I'm going to type that in exactly as I have it written. And I'm getting the velocity of that rocket is about 8.03. Now, if you notice the beginning of the problem, a spacecraft can obtain a stable orbit 300 kilometers above the Earth if it reaches a velocity of at least 7.7. So that is above our 7.7. So the answer is going to be yes. It can obtain a stable orbit 300 kilometers above Earth because it did get a velocity of above 7.7. All right, so that is it for chapter 7. So thank you for joining me. As always, please make sure you have everything written down so we can come back and do our practice work in class.